Hi everyone, good evening. I hope you're doing well, or I guess it's good morning or good something over there. Um, Today's topic is populations and the first and second laws of population ecology. So, generally speaking, a population, a group of individuals living in a specific area that's defined by the researcher, is really a fluctuation of recruitment of individuals through birth and immigration, and loss of individuals within that space through death, predation, right, and immigration out. So, how do we define it? First of all, a population is simply a group of interbreeding individuals of a specific species in a specifically defined area at a specific defined given time. And the issue with that definition to begin with is that we, as researchers, decide what our populations are. It could be the individuals living in a classroom, on campus, in a country, in a state, in a continent, or the entire human race, right? Our population is defined by the way we decide it. We can think about human population as being something that is fixed in, let's say, a given week, a year, a generation, a century, or even throughout the history of humanity since we evolved ourselves. So again, we've got to decide what it is that we are using the parameters to define our population when we talk about population. So how do we, what influences the size of the population? Well, that comes originally, or the population itself is what we call N. You've already seen this, I've used it multiple times in class, 1 over N times delta N delta T, or a per capita growth rate, essentially comes out of this definition of the concept of a population size. So how do we define it? Or how do we define a population size? We can count individuals, simply going in and saying there are 39 million people living in California, and there are half a million people living in Wyoming, okay, approximately. Which means I can go in and say all the individual humans living in the state are my population. But this always doesn't give us the best understanding of what our population is, or how to, or what influences it, or the conditions of the individuals living there. And as a consequence, sometimes it's better for us to think about it using density instead, which is the number of individuals living in a specific area. In this case, California has 97 individuals per square kilometer. But New Jersey, that has a much smaller population, only about 8 million people, has a much higher density of 467 per square kilometer. So you can see how, essentially, while we still had the most individuals of all states living in California, they actually live in a very spread out environment in relationship to, let's say, New Jersey or New York. In the same way that we can think about China having the biggest population on Earth, 1.4 billion, they only have 145 individuals per square kilometer. But in India, that has a lower population, 1.3 billion, the density is much greater, of 420 individuals per square kilometer. When I can't count, and I can't even estimate in a specific area, and I apologize about the noise, I don't know what's going on, I think it might be a protest outside here. We have an option of quantifying our population using biomass, or essentially how much carbon is stored in an area. If I cannot measure individuals, it's essentially be weight by volume, and says in, let's say, a vial, I have this much living material, right? So algae, insects, etc. Sometimes they're too many to count, so I'll use mass to quantify my population instead. And last, if I don't know where one organism starts and another ends, sometimes I might use a percent cover to estimate my population. Percent of shrubs in an environment, percent cover of dandelion lawn, or even percent cover of vegetation if I don't know what species are different species. I'm just going to use vegetation and use a population in this case. But again, ignore the last one. Actually, most of the time, it's not a great example because we want to try to stay with the same species. How does the population grow? Essentially, if our immigration and births are greater than the death and emigration out of my environment, right? Remember when we talked about genetic gene flow of genes coming in and going out. That's exactly what we're talking about here. Our population will grow. So I can simply use this information of birth plus immigration minus death minus immigration, and that gives me the rate at which my population grows, or what we define as R, or it's the intrinsic growth rate. Okay, so this we use as R, and again, how do we use it? What do we apply to this specific model? Again, a model is just a mathematical explanation of a pattern that exists in nature. Essentially, the intrinsic growth rate, sorry, but that really equals the change in the population size over time. Okay, and we're going to get back to that because that is our definition for biological fitness. So what are some typical growth rates, intrinsic growth rates of a field vole, for example, type of rodent? It is about 1%. So per generation, 1% of growth for that species. For a dog, it's about 1/9%. Okay, don't forget that a generation, okay, which is the average age of a newborn's mother, will be very different in a vole and in a dog. So dogs start breeding at about the age of 2, while field voles usually start reproducing at the age of 2 months. For us humans, it's about 1/3%, but for our generations are about 27 to 30 years. So again, the R itself does not dictate time, but how much per unit of time the population will grow. Just a second. Let me stop here a second too. Okay, I apologize for that. I think that was some kind of crazy right-wing protesters that are trying to shake up things around here and just screaming through megaphones down the highway. So I apologize for the noise. Anyway, back to our intrinsic growth rates. If the R values are 0, our population is stable. There is no change over time. And essentially, what dictates the size of the population in such a situation ends up being the availability of space or food. Okay, so resources in the environment dictate its size. And think about slow reproducing species like rhinos or pandas. It is literally that the environment cannot sustain many of them. So for everyone that dies, it's replaced by a newborn individual. When my R value, the intrinsic growth rate, sorry, not intrinsic, the growth rate is negative, okay, it's smaller than 0, then essentially my populations decline. There's not enough resources to sustain the population, and it's shrinking. There's not enough space for them, or there's too much competition between them, so the population is in decline. And of course, if it's positive, okay, then the population is increasing. One thing that I want to note also is that an intrinsic growth rate is a fixed value for a population or species, but different populations of the same species might have a different R that is specific to them. In other words, let's say pandas living in East China versus in Central China, based on different effects of human degradation of their habitat, might have a different R, even though as a species they still have the same R. So that leads us to the first law of population biology, which again leads us to what this R actually is. So again, the change in the population size, the delta is change in, so current minus previous divided by current time minus previous time for change in time, how much time has elapsed, okay, equals the R value times the population size itself. Okay, I can take that same equation and put it into a changing or continuous model that will allow me to track how things change over time. Okay, so remember, notice that we don't have a delta n. This time it's n of times t plus 1 to n of times t. In every time step of 1, we are gaining a certain amount. In this case, it is the population as it was times an exponent, okay, which is 2.145 something, just like pi. It's one of those numbers to the power of that r. So this I've already mentioned, that every population has its intrinsic ability to grow exponentially, where n is the population size, r is the intrinsic growth rate, and t is the unit of time, usually a generation. So that's essentially the first law. That essentially, if we don't have limitation to the growth, no effects, no intervention of the environment, populations will grow exponentially. They'll keep on growing at an increasing speed from one generation to the next. What does that look like for different R's? We had our field fold. So in 300 generations, we're up to 2,500, starting at about 10 individuals. We're up to essentially thousands of voles. For dogs, it's still pretty high. We're up into the about 1,500 dogs in a couple of generations. And for humans, in 300 generations, that is 1,000 years, from 10, we've only gone up to about 400. So a very slow growth in relationship to that. Then we can move from the first law to the second law, which essentially says the idea of limitless growth is unrealistic. So in other words, as our populations grow, they always will hit a boundary. There's only so much space, so much food, so much water that will limit the growth of those populations. So in other words, density, the first law is density independent. No matter how many individuals you have, they'll continue to grow at the same speed. But if we start changing that and adding the individuals and how the competition for resources affect them, okay, essentially the population will start slowing down in its growth. So initially they grow fast, and then they slow down. Sorry, there's noise again. I'm going to slow that, pause that again for a second. So let's recap here. Essentially, populations tend to grow exponentially. For every individual that's born into them, they grow faster. But essentially, this ignores competition for resources and lack of space in the environment. So the second one basically says that there's always, the second law always says that there's a limit to the growth and they cannot grow limitlessly. Okay, what does that mean? It means that essentially, because our populations start competing for the same resources, they will slow down and balance off. In other words, there's a density-dependent growth. Okay, growth is influenced by the size of the population. And for every individual born into the population, the growth slows down proportionally. So as the population nears the limit of growth in the environment, it will start tapering off and slows down significantly. So essentially what it tells us here, let me pull up my little marker again. Exponentially, it can grow very fast and goes to limitless growth. But if you add individuals when they start competing for resources, for every individual born, the speed, the angle of growth tapers down and comes down towards a level point or a plateau where it balances out on the total maximum capacity of the environment, which is called a carrying capacity. So I can take the same model. I'm adding in a K, which is a carrying capacity. The instantaneous model here has the K minus N, so essentially the carrying capacity minus the population size. As we add individuals nearing K, that becomes a smaller and smaller number, which basically tells us that the effect of R becomes smaller and smaller and smaller. But if we look at the continuous model, which is what's modeled in the graph over here, it's essentially the same thing, just with that k minus n over k that balances those dynamics. So where K is carrying capacity, there's a maximum size to the population that the environment can support, and the population can only get to that point. So what is a carrying capacity? How do we define those limits to the growth? First of all, we might have some abiotic sources: space, water, how much shelter or places to hide, nitrogen and phosphorus for growth of plants, light or energy for, again, growth of plants. The temperature in the environment can limit the growth and the speed at which organisms grow, and some catastrophes, some hurricanes or tornadoes or earthquakes. All of these things might limit the growth of a population. Some biotic effects that might limit the growth are availability of mates, the competition for resources, predation, how much predators are in the environment, epidemics, so pathogens limit the growth of a population and cause populations to shrink, and things like parasites. For example, we've got this water or aquatic isopod, like a potato bug, that eats the tongue of the fish and replaces it and eats part of its food as it goes. Well, that's a good example of how they're losing energy because of a living thing that limits their growth and decreases the value of the energy in their environment. All these together create a carrying capacity. Now, we can look at some examples here. This is an example coming from a reindeer in St. Paul Island, which is in Alaska, where we know that in 1911, 25 deers were introduced to that island, and by 1938, the population was 2,000. That is a beautiful graph for the exponential growth of the population. However, the competition combined with a harsh winter caused a collapse of those reindeer in what year was it? I think it was 2012 or no, sorry, 1940 sometimes. So you can bring it down. Yep, 1940, and you can see the population almost crashed completely. Another example of that is this in the Serengeti. Okay, there used to be a hunting that was limiting the population. So the population was growing exponentially. In that thing, the competition was low. We were hunting and removing a lot of individuals, and all of a sudden you remove it, and the population starts fluctuating around the carrying capacity of about 12 million individuals in the Serengeti when we removed some of the constraints and allowed them to get back to their natural population sizes. Some other examples of what we can predict, the model compared to the actual data. For example, we have paramecium, okay, type of protist. They follow the lines pretty nicely. You can see the dots being the actual populations being measured compared to the line, which is essentially what the model predicts. Daphnia, type of crustacean, a rudimentary, very simple crustacean, they actually surpass the carrying capacity and then crash down and balance onto it. In slower reproducing organisms, we have more fluctuation and they tend to overpass sometimes significantly, like this first seal over here. So once our populations reach the carrying capacity, a few things can happen. Okay, they can move into a fluctuation pattern. Okay, that will just be random or just go up and down based on random events. And we tend to call that irregular or dynamic, irregular population dynamics. And a lot of organisms like insects or small birds tend to follow these types of population dynamics that are kind of irregular. However, there are some more regular ones that can repeat themselves on a day-to-day basis or regular basis. For example, we have the cyclic population dynamics, okay, which usually are driven by predator-prey dynamics. So they will go up and down. As the prey go up, the predators will go up and consume them. And they'll tend to crash as a consequence of that. And they tend to be cyclic. They repeat themselves every certain amount of years. We call it, if it's a regular pattern that appears again and again and again, we call it a limit cycle. So if this has a top 1, 2, 3 back to the same point, that's a 2-point limit cycle. One high, one low, then back to one high. It can be over 3 points, 4 points, 5 points. My students in my conservation biology course right now are modeling ones that have sometimes 6 or 8-point limit cycles in their predator-prey dynamics and competition dynamics. This is an example here. You can see that what happens in a snowshoe hare and lynx cycle. The hare in blue, they go up. The predators follow a few years later. They go up as well. They then eat too many of the prey and crash, and the prey crashes. And then the lynx, the type of cat that eats those rabbits, basically crashes afterwards. Okay, so they'll go up, down, and they more or less fixed around that pattern. This is another example of one. This is a 4-point limit cycle, which does very similar dynamics. We might have a population that goes chaos or chaotic, okay? And basically what a chaotic pattern means that it goes up and down in a irregular pattern that does not follow specific fixed dynamics. And usually what leads to that might be multiple species of predators or both competition and predation. So a complex environment leads to more chaotic patterns or less predictable patterns in a population. Another thing that can limit things are epidemics, okay, which are disease-driven. The population exceeds its carrying capacity, then the density of the population gets too high, and that allows for good dynamics for diseases to spread, and they will crash. And then they balance off for a little bit and go high up again, and then crash. And then balance off, go back up, and crash. Human populations tends to do that very, very regularly. Okay, some examples of epidemic dynamics: we have a lot of invasive species that will consume a specific species of trees. Emerald ash borer, for example, in Illinois is killing all the ash trees. We had the hemlock woolly adelgid that climbed up the entire eastern coast of the United States, killing all hemlock trees. And these follows these regular patterns of a disease coming in, killing a lot of the population, it's balancing out at lower numbers, then starting to get back up and getting hit again. The bubonic plague was humans, killed half of the population of Europe in the 14th century, is another example of that. Then the European population balanced off for a while and then started growing back to the same levels and higher only in the 19th century. So it really curtailed the population of Europe for a very long time. You can see what happened here. It went back up to a certain high. And what's interesting here is that the limits to the growth or the limits to the population in Europe were actually driven by the availability of food. So as the Industrial Revolution began and food became more available, the population was able to really jump to a much higher level. And then another thing that kept it growing exponentially was the invention of penicillin and antibiotics. The last type of a system that exists is an episodic one, which basically is one that repeats. The population keeps at a low level and then jumps back up. It's exactly the opposite of the epidemic pattern. In other words, conditions happen to be just right at a specific year, and then a population skyrockets, and then things get bad again, and they crash back down. Okay, examples of that are like mosquito outbreaks that once every few years, you'll have a really bad mosquito year because the conditions were just right. And it's again similar to irregular, but it's essentially usually weather dependent. So the climate will dictate when those patterns occur. So again, the 4 kinds of population dynamics, just remember them, are irregular, cyclic, which is a predator-prey or competition, epidemic, which is led by high densities of populations, and episodic, which is weather-related or a climate-related pattern. And we'll leave it